Welcome to Module 2, and in this module, we will be reviewing certain conventions regarding the notations used to describe both stars and planets, as well as exoplanet transits themselves. We'll also look at some of the relationships between different star properties, and finally, we'll take a look at some of the properties of an exoplanet light curve.
So first of all, regarding the different properties of a star, these are often expressed not in absolute terms, but rather they're expressed in units relative to the corresponding values of our sun. So for example, M star, the mass of a star, is often expressed in units of the mass of our sun, radius of a star in units relative to the radius of our sun. Luminosity of a star is often expressed in units relative to the luminosity of our sun. And finally, temperature is often expressed in units of the temperature of our sun. Likewise, planetary parameters of mass and radius are often expressed in units relative to the mass and radius of Jupiter. Finally, different important transit parameters we should be aware of are, first of all, T sub c, which is the midpoint of a transit, F, the flux of a star, P, the orbital period of an exoplanet around its host star, and small a, which refers to the semi-major axis of the exoplanet's orbit. And this is often in terms of astronomical units, where an AU is the average distance between the Earth and our sun. There's an interesting relationship between the color or spectral type of a star and its luminosity, as well as between the spectral type and the temperature of a star. So based on the spectral type of a star, one can determine its temperature as well as its luminosity. What's indicated on this diagram, the so-called Hertzsprung-Russell or HR diagram, is the location of our sun, which is indicated with a luminosity of 1. So other stars are relative to the luminosity of our sun. As you notice, our sun is on what is called the main sequence of stars, and one can determine from the spectral type, as to say the color of a star, its temperature and luminosity. So this is a very important relationship among all three parameters of a star. Another important relationship is that the radius of a star is a function of its luminosity and temperature. So as we just saw, given the spectral type of a star, that is to say its color, one can get its luminosity, one can get its temperature, and then from the formula that you see here, one can estimate its radius. The radius of a star, our star, is very important because it can later be used to compute some important properties of an exoplanet, in particular, the radius of the exoplanet itself. And finally, there is a relationship between the luminosity of a star, or L star, and its mass, given by the formula that you see here, where M sun is the mass of our sun, which is known, and L sun is the luminosity of our sun, which is also known. So just based upon L star, namely the luminosity of the star, one can estimate the mass of that star.
And finally, if we look at some of the properties of an exoplanet itself, there's a number of relationships as well. First, however, the important thing to note is that there is two types of eclipses that take place with an exoplanet transit. As the exoplanet moves in front of the star from our line of sight, the light of the star is blocked, and that's called a primary eclipse. As the star then orbits around toward the back of the star, and the planet itself is illuminated, but then it goes dark as it goes in back of the star, we call that a secondary eclipse. What we'll be mostly concerned about in this course are primary eclipses, that is to say, when a planet moves in front of its host star. Notations used as far as the light curve are concerned are at least three. The duration of the transit from what we call the ingress point to the egress point is denoted by small t subscript capital T. The time at the bottom of the light curve is referred to as small t capital F. And the depth of the light curve, or the delta F change in flux, is referred to as delta F. There's, again, some interesting relationships between and among each of these properties. So, for example, the radius of a planet is a function of the radius of the star and the change in flux. The ratio of the orbit of the planet, namely A, small a, and the radius of the star, r star. That ratio is a function of the period, P, the change in depth of the transit light curve, as well as T, capital subscript capital T, and small t capital F. So the orbit of an exoplanet, knowing our star, one can determine A. And finally, the inclination of an exoplanet's orbit, or small I, is a function of the period, the change in depth, and again, the duration of the light curve and the duration at the bottom of the light curve. The formulas for coming up with these relationships can be found in a paper by Seeger and others in 2002. So that concludes some background on the different notations used with respect to stars and planetary properties, as well as some important relationships.